Time for another energy cycle, specific energy cycle piece of, revision, because there's another thing I was asked for. It's the link between the delta H values for lattice energy, solubility and hydration. Now you do have to know firstly what they are. They're things at A level that you have to remember. So lattice, you need to know that lattice energy is this one. So you take ions that are in the gaseous state and you turn them into the solid material. Example would be sodium ions, fluoride ions, and the solid is then sodium fluoride. So that's delta H lattice. Same issue as I have before. In fact, you'll find in modern books it's written as that. I have real trouble with that, as you probably saw me trying to write it badly there. So delta H lattice, or delta lattice H, doesn't make sense to me that. So that there is one of the definitions you need to know. Lattice energy, gaseous ions turned into a solid lattice. This here is the enthalpy change on dissolving that solid lattice. Now there's a lot of things about what's all that really about. It's about dissolving 1 mole to infinite dilution and all this kind of thing. Yeah, you can look all that up. This video is really not about all the definitions, it's about how you use this cycle. This is another example of a Hess's cycle. So delta H solubility, or SOL for short. So that's the energy change of doing that. Often that energy change isn't particularly large, although for some substances it is noticeably large, like sodium hydroxide for instance. It gets the water really hot. But a lot of the times for neutral substances certainly the values are quite modest, I think would be a good word. And then down here is, I'm going to use a mathematical symbol. That is the Greek capital sigma, which means sum of. It's the sum of the delta H hydrations. So whichever ions you've got up there, you get the delta H hydration values and combine them and you'll get the value for down that side. Now that's all a bit airy-fairy because there's no actual chemicals there. It's much easier if you see it with some real chemicals. But this cycle of gaseous ions, solid lattice, ions in solution in the cycle with the arrows in the directions that they go, bit of an issue with lattice energy. Some courses define lattice energy going the other way. Almost all courses have it going that way, and I have to say that is therefore the most common way to do it. That way is a negative value because it's exothermic. It's always therefore endothermic, same size, opposite sign, going the other way. I'm going to be doing it in the way that I teach it because that's what this is for. So there we have that. I'm going to do this with a specific example and we're going to use it to answer a question. Yeah. I need to clean the board for that, so I'll be back after we've done the cleaning the board. See ya. So, relatively straightforward example in terms of complexity of salt. Sodium chloride, 1 sodium, 1 chloride. Going to use it to calculate the solubility enthalpy change, the enthalpy change of dissolving sodium chloride in water. So, got to set up the cycle correctly. Na plus Cl minus ions at the top, NaCl solid down the bottom. Lattice energy goes down there. It has a value of minus 780 kilojoules per mole. That's a negative value because we're coming down from the gaseous ions and putting the lattice together, forming bonds. Coming down the other side is the hydration energy of sodium and the hydration energy of chloride. There's one of each, so you sum just one of each together. And they have those values, and the answer of summing the two together is minus 769. So we need to do from that end of the arrow to the arrowhead, so we need to go the roundabout route. So it is the wrong way up the lattice energy. So the wrong way means it will be plus 780. And then the correct way down the hydration side, which is plus and then minus 769. And when you do that, you get plus 11, and it's in kilojoules per mole, plus 11. I encourage you to put a sign on, make sure you've thought about the construction of the energy cycle and getting the sign right. Plus 11, like I said, not particularly large value. There's the enthalpy change of solution. We'll do a marginally more complex one second, but as always, you know, I need to take a little edit in order to save some time. See you in a moment. So, slightly more complicated example, slightly different question. Calculate a hydration energy for, in this case, the magnesium 2+ ion, using the information that you're given. I've set the information out in a question. Obviously you would probably get them listed, and you need to be able to construct this cycle, put the values in the right places with the arrows in the right direction, which I mentioned before. So the lattice energy will be, we're forming MgCl2 there, so we need Mg and we need 2 chloride ions now. So Mg, 2 chloride ions makes MgCl2. Quite a large lattice energy value, but because of the way I do lattice energies, it's very exothermic. Dissolving MgCl2 into water will produce Mg2+ ions and Cl- ions, except that in this we need to remember there's a 2. And that has a value of -155, which means that as we come down here, this is the value we're trying to calculate, and this we need 2 of. So we need 2 of the 363, because 363 is the value for chloride. And that means that you put those together, it's -726. So it's that value, this value, and this value that we're going to piece together. So we now are working on this arrow, because this is the one with the missing value. It's not the entire of that side that we're looking for one of the components of that side. But we're going to go from that end of the arrow to the arrowhead, which has converged into a 2 down here. So we're going to have to go round that way. So that means that we go down there in the correct way, 2526. And then we go the correct way there, plus -155. But this is the little tricksy bit, I suppose, is that it equals delta H hydration Mg2+, gas, takes so long to write, plus -726. So we're summing together, and there'll be negative values, and we're summing together negative values. So what you then have to do is work that out. So that there is -2526 -155 plus 726. So take that over that side, and you put that together. So let me look what the answer is, save me working it out. It's -1955 kilojoules per mole. It's a large value. Why is it a large value? Because Mg2+ is a 2+ ion, and magnesium ions are really small, so it's going to pull things in really tightly and strongly and form strong bonds. So it is a value of -1955, not the year I was born, don't you dare. So, just to recap, when you've got one of the components missing, that's the arrow you work on. You go round from one end of it to the arrowhead end, construct it with the missing value, rearrange, end up with that. Now if you want more practice, there will be some practice questions with answers attached to this video, either in the blurb that goes with the video, or if you're one of my students, you know how you'll get it sent. If you want even more practice than that, you're going to have to wait for book 4 of this series of books to come out. You might notice the author. It's myself. And 2 of these books are available on Amazon at a very reasonable price of $7.99 right now. Book 4 is the one with all the enthalpy but other energy stuff in as well, so it covers stuff in year 13, so it's good value for 2 years worth of study. Think about these books, answers are in there, but they're not just the answers, they're fully explained how on earth you get to that answer, because when you go, oh, what did I do wrong, you often don't know. That's what these books are for. So there we are, the link between lattice solubility and hydration enthalpies. I'm sure I'll see you again soon with well, further revision materials that have been asked for. Thank you very much, see you soon, bye.